Today, we're diving straight into the invisible forces that literally shape our physical world. I absolutely love unpacking these everyday mysteries because the underlying answers are always so much more fascinating than we expect. We are going to explore the mechanics of magnetism, and to do that, we're actually going to start right in your very own kitchen. Think about a highly relatable puzzle for a second. You grab a standard, everyday red and blue bar magnet. You walk up to your refrigerator, let it go, and smack. It snaps right onto the metal door, completely defying gravity. But if you take that exact same magnet and press it against a wooden kitchen cabinet, it completely fails to stick. It just drops right to the floor. So why is that? What's actually happening on a fundamental level that makes one material welcome this invisible force while another just completely ignores it? Let's look at a few more examples to really frame this up. Take a standard iron nail. It immediately and aggressively attracts our magnet. But then look at a copper wire, a piece of aluminum foil, or even just the stainless steel spoon you'd use to eat your cereal. With those, there's absolutely no reaction. Nothing. So it's not just a simple matter of metal versus non-metal. It's about specific types of metal. To figure out why some materials have this magnetic superpower while others are entirely inert, we have to look much, much closer. To solve this mystery, we're leaving the macro world of the kitchen behind. We are going to shrink way down and take a journey deep inside matter itself to discover what fundamentally gives a material its magnetic properties. As we float through this vibrant 3D atomic space, remember the golden rule of physical science. Literally everything is made of atoms. Every single object around us is built from these beautifully organized, glowing building blocks. But to figure out magnetism, the atom itself isn't the smallest piece of our puzzle today. We have to peel back one more layer. Zooming in even closer to a simplified model of an atom, we find electrons. These are constantly moving, spinning particles, just perpetually orbiting the nucleus. But it's not just their orbit that matters here. It's the fact that these little particles are also constantly spinning on their own axes. And here is our first massive breakthrough. That spinning motion actually generates a microscopic magnetic field. Every single one of these spinning electrons behaves exactly like a tiny magnet, complete with its very own miniature north and south pole. That means the fundamental building blocks of all matter are literally packed with infinitesimally small magnets. Okay, but stop and think about that for a second. This brings up a pretty massive question. If everything is made of atoms, and atoms are full of spinning electrons, and every single electron is a tiny magnet, why isn't your wooden cabinet magnetic? Why isn't your cereal spoon constantly pulling on your bowl? Why isn't absolutely everything in the universe just sticking together in one giant magnetic clump? Well, the answer lies in teamwork, or honestly, a total lack of it. In most materials, like wood or aluminum, these tiny magnetic arrows are pointing in completely random directions. It is pure chaos in there. For every electron pull in one way, there is another electron pulling in the exact opposite direction. They're locked in this invisible battle where their forces just cancel each other out. The result? Zero net magnetism. But let's pull back and focus on our iron nail because iron is special. The internal structure of an iron crystal is completely different from wood or copper. It is beautifully organized. Iron doesn't do chaos. It does structure. Inside iron, billions of atoms group together into these highly distinct glowing zones called magnetic domains. Within each of these microscopic neighborhoods, all the tiny magnetic arrows actually agree with each other. They align perfectly, pointing in the exact same direction. So instead of millions of individual electrons fighting, they work together, basically acting like one miniature bar magnet hidden deep inside the metal. There is a catch, though. Even in a piece of unmagnetized iron, these neighboring domains might be pointing north, south, east, and west. So domain A cancels out domain B, and domain C cancels out domain D. The overall macro-level magnetism of the iron nail still sits at zero. The forces are highly organized locally, but totally randomized globally. That is, until something comes along to wake them up. Now watch exactly what happens when we bring a magnet nearby. By introducing an external magnetic field, those previously clashing domains smoothly rotate. Guided by this new, powerful external force, they completely abandon their local directions and begin pointing in the exact same direction as the magnet we brought close to it. As that external magnetic field strength increases, more and more domains fall into line. The entire block of iron practically glows with energy as it transforms. It is no longer just a collection of random clashing domains. It has become one powerful, unified giant magnet in its own right, suddenly capable of reaching out and snapping up smaller objects like paper clips. This powerful alignment behavior, this incredible ability of domains to flawlessly line up and act as a team, is the entire secret behind why our fridge magnet sticks to the door. In physics, this highly receptive behavior is known as ferromagnetism. It is absolutely the gold standard of magnetic attraction. It's fascinating to see how this builds across the entire material spectrum, because materials react in fundamentally different ways based on their atomic structure. We have ferromagnetic materials, like iron, which exhibit that incredibly strong, violent attraction. Then we have paramagnetic materials, like aluminum, which barely react at all. They feel a super weak attraction that you'd practically never notice. And then, most surprisingly, we have diamagnetic materials, like copper. Copper actually generates a weak repulsion. Introduce a strong enough magnet to copper, and it literally pushes back. But going back to our highly cooperative ferromagnetic iron, it has one more magic trick it can perform. Sometimes, even after that external fridge magnet is pulled away, those atomic domains remain completely locked in their newly aligned state. They refuse to go back to chaos. They basically freeze in place. This phenomenon, where the material remembers its magnetic alignment, is called a hysteresis loop. And this is exactly how the permanent magnets we use every single day are manufactured. Zooming all the way out from the microscopic world back to our human-scale world, it is so vital to recognize the sheer scale of this phenomenon. These tiny, perfectly aligned atomic domains aren't just a neat parlor trick. They are the literal, invisible engines powering monumental modern technology. Without these synchronized atomic arrows, we just wouldn't have the spinning wind turbines generating our power, MRI scanners, electric vehicles, or even the hard disks storing data in the smartphone you're probably holding